All right, you ready?
Yes.
Sweet. I want to start off talking about the Doppler effect. The Doppler effect that we have done so far is all qualitative.
Mm-hmm.
It's all conceptual, and but there's also a quantitative description of the Doppler effect.
I think I remember you telling me about this. Yeah.
So the Doppler effect results from relative motion. It's relative motion between a source and an observer. If there's no velocity, then everything's whatever the frequency is, the wavelength of this is what the observer hears. However, if there's relative motion between the two, then things become different. Mm-hmm. Okay, so remember, speed is distance over time. So the speed of sound, the velocity is the wavelength divided by the period of the wave, and that's 343 meters per second. So when the siren comes toward the observer gets a different wavelength. Mm-hmm. So you got this shorter wavelength. Mm-hmm. And so how do you establish what that is? Well, it's the wavelength of the source minus the velocity of the source times the period.
The wavelength.
That's velocity times period. So that's the difference between this. That's the wavelength that the observer hears.
Got it. That makes sense. It's just some subtraction and then a substitute equation in there for it.
Now, what's the relationship between period and frequency? They're inverse.
Yeah.
So
okay.
Solving, putting is velocity over that originating what the observer hears. The frequency of the observer is the velocity divided by the wavelength.
Okay.
Velocity divided by the wavelength. Let's see. Velocity is wavelength over frequency,
which is v
wavelength times frequency. So all this does is just solve for the frequency.
Okay.
Divided by the wavelength.
Oh, I see.
And that's
and
this is what the observer hears. So, and then this wavelength that the observer hears is this. Okay.
Got it.
So now, the math behind here is not important.
Yeah.
But this is the speed of sound, and the wavelength from the source minus the velocity of the source times the period gives us that wavelength. And what are we talking about? We're talking about this right here.
Okay. Yeah.
Okay. All right, and now math magic happens. And what we do is just, how can we express the frequency of the observer here in terms of the frequency of the source? All right, and here's the relationship. If you do some manipulation, you do some substitutions, and what you have is, this is the velocity of the source, and this is the speed of the sound. Mm-hmm. Well, let's tell what the heck does that mean? Well, what if the source isn't moving? Mm-hmm. Then that's 0. Mm-hmm. And 1 minus 0 is 1, and 1 divided by 1 is 1.
Frequency is the same.
What the observer hears is the frequency the same. So what happens if this starts moving? Well, now you have a fraction, okay? And that's going to take away from 1. So you'll get a number on the bottom that's smaller than 1.
Yeah, it's going to be a negative number, okay.
No.
No?
No, because unless it's going faster than the speed of sound.
Oh.
This is the speed of sound.
Got
this
it.
is the velocity of the source.
Got it.
So if it's going the speed of sound, if this is 1 minus 1 is 0 on the bottom, and you don't hear a frequency, that's where you get that sonic boom.
Yeah, okay, that's making sense. So what it tells you is, it just tells you that the frequency is going to be less or more. Right? Is that right?
Yeah. So let's say the speed of sound is 343 meters per second, and you're going 100 meters per second. So
then
that's
it's
3.100 divided by, it'd be the other way. Let's see, it's going to be.
Oh yeah, you're right.
100 divided by 343 is 0.29. So 1 minus 0.29 is 0.71.
Okay.
So this would be 1 over 0.71, and 1 over 0.71 is 1.4.
Yeah.
Equals 1.4. So you're going to hear a frequency that's 1.4 times faster than what you're hearing.
Yeah,
So,
because it'll be a ratio if you were going to divide it all.
yeah, we're not
Okay.
going to use this, but the
It's a
really
thing.
important point is that equations convey ideas, and you can have a lot of information in a compact thing here as long as you understand what's going on.
Yeah, that makes sense.
All right, now let's get into it. Newton's laws and classical physics hold true at the human scale. Is this on the thing there?
Yeah, yeah.
Okay. All right.
It's
at
cool,
the
I can
human
just- I'm just
scale,
setting
now,
it
what is
here.
the human scale? At our size, our velocities, and our time intervals. You know how it's like. Do hummingbirds have experience of time that's faster than our experience of time? You know what I mean? 'Cause
Yeah.
do they? And that's a legitimate question.
Yeah, I guess we'll never know.
So there's three things. There's the magnitude of our size, the velocities that we can attain, and the time intervals that we're used to. However, at very high velocities and at the atomic scale, the universe works very differently and doesn't conform to our intuitive expectations. Okay, there's two things that deal with this. Quantum mechanics describes a function at the smallest scales, and special relativity rules the domains of velocities not near the speed of light, but once you get up to about 0.4 times the speed of light, things start to happen. Now, you hear the things about the great grand unification theory. It's where we're unification, trying to put everything together, and that's hard.
Yeah, I have actually never heard of that, the grand unification theory.
Grand unification. That's because we haven't come up with it yet.
Yeah.
That's why.
I was like, I haven't heard that word before. One more.
Okay, special relativity, and this is the idea, considers the nature of a viewpoint called a reference system. So you're observing the shuttle. Tells you how old this is. Take off, and from the person that's standing on the ground, they see one thing. If an observer on an airplane watching it go by is going to see something else. They're going to see it going up, but they're also going to see it going by like this.
Oh, okay, yeah.
So
And
the idea of reference frame or point of view is at the heart of special relativity.
Okay.
Okay, there are two postulates. The first one is the laws of physics are the same in every inertial reference frame. And now what we're talking about, the laws of physics, is the classical laws of physics are the same in every inertial reference frame. And what the hell does that mean?
Yeah, what's an inertial reference?
That means you have a reference frame that's not accelerated. For example, here's inside of a box on wheels, and if this is a carriage standing still, and you toss a ball, it'll follow a path that you expect it to. All right, and if something is falling, it'll fall straight into the thing. The candle flame goes up. All this other kind of stuff. I don't understand the dog and all that kind of stuff. If the carriage is moving at a constant velocity, there's no acceleration, and if you're inside the box, you can't tell. As long as there's no bumps or anything, you can't tell if you're moving or standing still.
Yeah.
And so if you toss a ball, you get the same trajectory. Water still falls straight down. And I don't know what the rest of this stuff. Oh, and the light bulb hanging from the ceiling hangs straight down. Now, if it's accelerating, then the light bulb is going to go this way.
Yeah.
Because of its inertia.
Yeah.
And a ball that you toss is not going to go the same direction. It's going to follow a different path. And the water that's dripping down, because it's accelerating, is going to miss.
Yeah, and we all have I've experience with not necessarily that, but that idea.
Yeah, exactly.
Yeah.
So, and what is an inertial reference frame? That's where all the laws of physics are obeyed. This is fine. This is fine. But if you're in a box, you can't tell what's happening. But if all of a sudden, you look up and the thing is going this way.
Yeah.
Shouldn't be like that. Or if you toss something and it doesn't follow that path.
Yeah. That is not an inertial reference frame.
This is not an inertial reference frame.
Yeah.
These laws of physics that should happen are not happening here. Okay?
Okay, I think I got
So
it.
that's what an inertial frame. So relative velocities. Now we talked about that with the Doppler effect. velocities can only be measured between objects only.
Okay, that makes sense now.
The idea of absolute rest or absolute velocity is meaningless because what's your reference frame? Well, I'm walking at 2 meters per second. Yes, but the Earth is spinning.
Yeah.
Oh, well, the Earth is spinning. The Earth is traveling at this velocity, but it's going around the sun. And okay, it's going around the sun, but the sun is moving through the galaxy. So, in order to absolutely describe something, and the absolute description of something is very important in science, you can only talk about relative velocities. Okay, and that's where we're going. Okay, the second postulate is the speed of light.
So the first one was relative velocities and inertial reference frame. Understanding those two aspects, right? That's what we just said.
The laws of physics are the same in every inertial reference frame.
Got it. The laws
Okay,
of physics are the same.
The first one, in a non-accelerating reference frame, the laws of physics work.
Got it. Okay.
Okay. Now here's the other thing, and this is the big leap here.
Okay.
That the measured speed of light is always the same, regardless of the relative velocity between the light source and the observer. Okay. So you may get a frequency shift. You may, but the velocity of light, if you measure it, will not change, regardless of if this light is coming towards you or not.
Oh.
You know, hold on a second. Okay, there was this idea, because light was thought to be a wave, that waves have a medium to travel in, like air or water or slinkies or something like that. And so it was postulated that there was a medium that light traveled through called the luminiferous ether. Luminiferous ether that permeated the universe. It's like the phlogiston theory. You ever heard of the phlogiston, where heat was a fluid that flowed?
Oh, okay. I've heard that concept. Yeah.
Heat is a fluid that flows. It's not a fluid, but that's the idea. And so the whole thing, it's like dark matter and dark energy. I don't know what it is. We'll call it dark. And it's the same kind of thing. And the idea was there was this luminiferous ether that permeated the universe that the Earth traveled through. So a guy named Michelson who made this interferometer where, well, I'll show you a picture here. An interferometer where you've got a light source and a beam splitter. It splits, part of the beam is reflected, part of the beam is transmitted. Okay, so, and then you've got a mirror here. And you have a path length here to here, and a path length here to here. And if the waves follow the same length, this length is the same as that, then they interfere with each other constructively to get a bright spot.
Oh, okay, yeah.
And you can move this back and forth half a wavelength, and you'll get cancellation, you'll get destructive interference. So this was Michelson's interferometer.
And there's ether wind over there.
Now the idea is that the Earth is traveling through the ether. It's like when you run, you feel you're going so fast, you're making your own wind, okay? And the idea is that the light in the ether, it's like if you're riding your bicycle with the wind, there's no wind. And if you're against the wind, there's hella wind.
Yeah.
So the idea is that if you're going into the ether, then the velocity of light will be less than it is if it's going perpendicular.
Okay.
And so they did this experiment, and it was very precision instrument because the difference in the wavelengths are very small.
Yeah.
So here's the deal. They measured the speed of light parallel to and perpendicular to the path the Earth followed through the ether. There was no change.
It was the same. Okay, I was going to ask, was it the same or no?
There was no change.
No.
It doesn't go faster or slower when you go with or against
it. Sorry, no luminiferous ether.
And if you think about it, what direction is the Earth going in its rotation, in its orbit, and then what rotation is the Earth? So you had to wait until the Earth was going around the sun in this direction and around in this direction, so you're very out.
Yeah.
So that the motion through the ether would be like this. So So smart people checking closely, no luminiferous ether.
Boom. That's why we haven't heard of it.
All right.
That's why I haven't heard of it.
All right. So, well, yeah. And so they're relativistic phenomenon. There are 4 or 5 here. I can't remember. First, and the most important, and this is probably the only thing that they're going to care about on the CSAT, is the idea of time dilation. And that is a moving clock ticks more slowly than an identical stationary clock.
Okay.
You got 2 clocks that are identical. You send one to the moon and back. The one that went to the moon and back will not show as much time passing.
Yeah. Okay.
Okay, that's time.
And I've heard that a couple of times now, so it's sort of sinking in there.
Yeah, and
should we watch it on here or on the over there?
oh, we can watch it. This is all whatever.
Oh, that was a bad one. Oh, gross.
All right, here we go.
Einstein's theory of special relativity was first written down over 100 years ago. Among other things, it describes what happens when 2 people are moving with respect to one another and how they experience space and time.
You sit down.
While the theory has been verified countless times over the intervening decades, much of it remains difficult for some people to accept. It predicts some pretty weird things that are just outside our normal experience. Perhaps the prediction that is most counterintuitive is the idea that 2 people can experience time differently.
Yeah.
Now, I don't mean that in the way that a small child waiting for Santa Claus to come complains about how long it takes, nor how someone dreading a dentist appointment finds that time disappears in the blink of an eye. No, I'm talking about the very strange claim that if you take 2 identical people wearing 2 identical and perfect wristwatches and arrange them to be moving with respect to one another, they will find that they disagree on how fast time is moving.
Whoa. Really?
Now, that just sounds really hard to believe, and it's definitely counter to our experience. But this isn't a theoretical idea. It's something that particle physics experimenters encounter all the time. So I thought it might be helpful to describe to you one such measurement using one of Fermilab's neutrino beams. You're going to have to trust me on the numbers I use, but the basic idea is incredibly easy to understand.
I trust you. Wear glasses.
So here's how it goes. To make a beam of neutrinos, you start with a beam of charged pi mesons, which we also call pions. Pions are nice because they decay essentially 100% of the time into a muon and a neutrino.
Okay.
It's also nice because pions are the most commonly made particle when you slam a particle beam into a target. This makes it possible to make tons of pions and, consequently, tons of neutrinos. The lifetime of a pion is easy to measure. Suppose we make a bunch of pions that are stationary. We find that they live a characteristic amount of time before they decay. They live 28 billionths of a second. Some live longer and some live shorter, but on average, that's how long they live. Now, we don't intentionally make stationary pions very often. It turns out that they just aren't all that useful. Instead, we make them with lots of energy, and they're going very fast. We can measure their speed by just measuring how long it takes them to travel some known distance. Take the distance and divide by the time, and you get the velocity. At high energy, the pions move at almost the speed of light, which is about 300 million meters per second, or for us Americans, 186,000 miles per second.
Ew.
If we know the pion's lifetime and how fast they're moving, it's easy to figure out how far they move before they decay. Just as a car moving 60 miles per hour for 3 hours will move 180 miles, you multiply the time and the velocity to figure out how far they go. So when we multiply the velocity of 300 million meters per second by a duration of 28 billionths of a second, we get 8.4 meters, or about 27 feet. So if we had a beam of pions and we wanted to let them decay into neutrinos and muons, we'd have to give them at least 27 feet of distance to let the average pion decay. If we wanted to leave long enough for the laggards to decay, we need to give them a longer distance. Call it 60 feet, which is the distance from pitcher's mound to home plate in American baseball. If that's all there was to it, we'd be done.
Really catering to Americans
there's
here.
more to it than that, or I wouldn't be making this video. And that is the effect due to relativity. You see, what I've told you is the time it takes for pions to decay according to their own watch. We experience time differently. For us, time passes more quickly. So just how much more quickly does time pass for us? Well, the answer to that is actually kind of tricky. It depends on the energy of the pion, which is something accelerator scientists can change at will. However, for the specific pion beamline that we use at Fermilab to make a neutrino beam that we send to northern Minnesota, a realistic beam energy is 10 billion electron volts of energy. I'll show you how we determine the difference in the rate at which the pions in our clocks tick, but I must caution you. Doing this right means that you need to know your relativity. I get lots and lots of emails from people who misuse relativity. So before you generalize, remember, I'm a paid professional. Don't try this at home. Or, if you choose to do so, be sure to do it correctly. It turns out that you can determine the difference in the rates of two clocks by dividing the energy of the beam of pions, which we recall is 10 billion electron volts, by the mass of the pion, which is 0.14 billion electron volts. Do that division and you get 71.4.
Okay.
So that means while the lifetime that the pion experiences, which is 28 billionths of a second, is much longer for us, specifically 71.4 times 28 billionths of a second, or 2 millionths of a second. And since the speed of a pion with that velocity is near the speed of light, it means that as far as we're concerned, the pion will travel 600 meters, or 1,920 feet. That's over a quarter mile. 36% of a mile to be exact. The reason is simple. Our clocks tick more quickly than the pion's clock. So this might be confusing, so let's recap.
Yeah.
We can measure the lifetime of a stationary pion, and it's about 28 billionths of a second. A particle with that lifetime, traveling at the speed of light, will travel about 30 feet, which is about from here
I cannot take him in his glasses,
to here.
seriously.
However, the rules of physics are a little bit different for a pion traveling at high speed. A pion with an energy of 100 billion electron volts doesn't travel 30 feet, not by a long shot. It travels more like a quarter mile, which is like from here to...
This is why he's out of breath in this video.
He's probably done it once already.
Yeah, exactly. Like...
here. So no matter how much Einstein's theory of special relativity bothers you, the data is inarguable. Moving clocks tick more slowly than stationary ones. We demonstrate this every 2 seconds with every blast of neutrino sent from Fermilab to distant detectors. There is simply no argument against this irrefutable data. While the predictions of Einstein's theory are broader than this single observation, it's the simplest way to confirm his theory. The other predictions have also been confirmed, but we'll leave those stories for another time. However, the bottom line is that our intuition that all clocks tick at the same rate is simply wrong, and Einstein retains his place among the pantheon of physics superstars.
Feynman.
Okay, so wait. So they said so if you're moving faster, time goes slower. Right, because she's walking.
For your reference frame.
your reference frame.
For your reference frame, it doesn't change.
Yes. Yeah.
But if you have two clocks,
You
and
compare.
you go somewhere,
Another
and
person
you
doesn't.
come, and the other person stays there, and you're now 10 minutes behind them because of the velocity.
So how come our iPhones are all in sync? Because it's not.
How fast are you going?
I don't know. Not fast enough. We're all going the same speed, technically.
All right, now check this out. How much time sound slows down relative to a stationary viewer? Look at this.
Wait, how much time slows down relative to? Okay, yeah. Oh,
Okay,
there's
so-
same equation.
So
Similar.
here's the time that you're carrying with you. Mm-hmm. Oh, wait a minute. And this is how much it changes.
Or the time of the observer, like the person walking fast and the person not walking.
You know, that's an excellent question. I screwed up there. Well, let's take a look if we can figure it out.
Okay.
All right, if it's 0, the velocity is 0, then it's going to be 1. You know,
1 minus 0.
1 minus 0 is 1, square root of 0. The time interval for one clock will be the same as the other.
Yeah.
Okay, but we want to know how much. So this is the moving, and this is the
Chilling.
observer.
Yeah.
Observer. You were right.
Yeah.
Okay, so and what this is the same
As that, yeah.
as
over
what we
there.
were doing before, and it has to do with relative motion.
And you could put the same numbers in there, and it would be a ratio.
And
well, not the same.
what happens if something's going at the speed of light? Then you get 0 on the bottom, and all mathematics collapses. So that's also something else Einstein said, which we'll get to in a minute. All right. So, but this, using this is
All
irrelevant.
mathematics collapses.
Here is what CSET wants.
Yeah.
The GPS system uses satellites which carry highly accurate atomic clocks. They've got atomic clocks.
Oh,
up
that's
there.
how.
Yeah.
That was motherfuckers.
And the receiver, your GPS receiver, measures the time light travels from each satellite. So it gets to the receiver with a time stamp, and the receiver checks that against its time stamp. And so it can say how far from this satellite.
Yeah.
And how far from this satellite, and how far from this satellite. And so what you get is you get a circle, and where they intersect.
Not 3, but 4.
But here's the deal. Multiple satellites increase the accuracy of the location. And so this locating, it's basically geometry.
Yeah.
All right? But here's the deal. Because these geostationary satellites are going 40,000 meters per second, relativistic time dilation must be factored in to reduce location error. So remember that question they were asking about GPS?
Yeah.
Here it is.
Okay.
So there has to be a calculation based on this velocity.
Okay. Using the previous equation that we just looked at.
Yeah, which we don't have to use.
Yeah.
We're not going to use this, but that's what's going on.
Okay, so they've got these GPS satellites up there with highly atomic clocks. They're moving, so they have to factor in that relative velocity.
They are going slower than the clock on the ground.
Yeah. Okay. Yeah. Oh.
So they're going slower than the clock on the ground.
Yeah.
So they have to figure out how much slower.
Yeah, to compensate for it.
So they can make a correction to establish exactly where it is. Now, if you're driving to someplace you've never been, you can put it in the GPS, it'll say turn left, now arriving at, and you might not be there yet, or you might have just passed it. It doesn't matter. But if you're in an airplane that is, you have to land in Hawaii.
Yeah. Hawaii.
You have to make sure you're in the right spot.
And so it uses the time and the speed of light.
So in the CSET, how does special relativity apply to GPS? Here it is.
Yeah.
Okay. Now we're going to blast through this rest of this stuff. Another relativistic phenomenon is length contraction. Viewed from Earth, a spacecraft traveling at relativistic velocities has its length shortened in the direction of travel. What the? So here is a sphere. It's just sitting there, and it's a sphere. As it goes faster, 0.3 times the speed of light, it's a little bit narrower in this than this. At 0.6 the speed of light, it's even more. And at 0.9, it's compressed laterally. So
I've heard this a few times too now, and it's making sense. I mean, it kind of makes. I mean, it in order to remember, it makes sense because you're going faster, you're getting more squished, But
the thing is, we can prove this mathematically, but they're not going to ask you to do anything. You just need to
it'll
know
be a
the
conceptual
concept.
thing. Yeah.
This one, you're not going to have to worry about relativistic momentum. Your relativistic momentum for things going far is faster than is larger than non-relativistic momentum. Don't even worry about it.
Okay.
This.
Oh yeah, this is in a video that I
This
watched.
is the big idea.
Okay.
This is the mass energy equivalency. This comes out of special relativity. Okay, and the idea is there is the rest energy of whatever you've got, and that's equal to mass times c squared.
Yeah.
Okay, that's the rest energy. But if it's moving, you have rest energy plus kinetic energy. And if you're looking at, if the velocity is 0, then it's 1 minus 0, and the square root of 1 is 1. It's just mc squared.
Yeah.
But as the velocity increases, this is going to get smaller on the bottom, right? Because you're going to get smaller, that meat, and since it's on the bottom, the total energy will get larger. So you've got rest energy and then the total energy. And this is, we'll come back to this when we get to chemistry.
Okay, so you said the faster it's moving, the faster moving it's going to get smaller, the more energy.
The more energy it's going to have. And that's just like conservation
that makes sense.
momentum.
Yeah.
But the new idea is this idea of rest energy. You know, you've got potential energy. That's not what we're talking about. It's not kinetic energy. It's just sitting there. There's energy. Doing its best.
Existing.
Okay, and so I don't even know if I should put this in here. Kinetic energy is the difference between the total energy and the rest energy.
Okay, I mean that statement makes sense.
Yeah, I mean, it's not a big deal. And any change in the rest energy causes a change in the mass.
Yeah, so this is a new concept because we never talked about changing mass. And I remember watching a video and I was like, what? The mass changes? Okay, so we'll keep going. Any change in the rest energy causes a change in the mass.
Okay, and we'll see this when we get into the mass defect.
Okay, I've heard that before.
All right. Now here's something wild. When the matter and antimatter, right?
I've heard the words.
When an electron and a positron meet, okay, that's matter and antimatter.
Okay.
They are annihilated. And
What a great word.
they change into a gamma ray,
Okay.
whose energy equals the total energy of the particles.
Okay.
So what does that mean? Well, you got the energy equals mc squared, the mass of this, times the speed of light squared, for one. And since they have the same mass,
Yeah.
okay, and then you have this gamma ray that comes out. It's a very energetic beam of light.
Yeah, I'm familiar with gamma rays.
Then, so matter is converted into energy.
Yeah, okay.
And now here's a wild thing. If a gamma ray passes close to the nucleus of an atom, it disappears and positron-electron pairs emerge.
Oh, so it can go both ways.
Energy can be converted into matter.
Okay.
Okay, now this is only at the very small scale
Yeah.
and at very high speeds. So,
Phew. Is that it?
that's it.
All right. So some of the big things we talked about were, I mean, I think the one the GPS. So the GPS and the time, and then the velocities, and then the mass.
And yeah, and there is so much more to this, but you
Yeah.
don't need it.
Yeah. I think I'd have enough to kind of make it through. It's hard because I really don't think they asked that many questions
They're
specifically
not,
about this kind of stuff.
But if this will help you make
Yeah.
sense out of this, and you'll have at least heard of that.
Yeah, because the geostationary satellites are traveling at 4,000 meters per second orbit relativistic time.